Hi everyone! This video is roll center part 10, and we will introduce the idea of finding the force roll center when lateral acceleration gets larger significantly. When the suspension geometry is asymmetrical due to significant lateral acceleration, there is still no definitive theory as to how the lateral position of the roll center can be clearly determined. However, looking at different ideas for locating the roll center will help you a lot to understand the roll center of a vehicle that is subjected to large lateral forces. In this video, I show you the idea of finding the roll center when the suspension geometry becomes asymmetrical due to large lateral forces. For the sake of efficient explanation, let's assume that the vehicles described here are symmetrical with respect to central longitudinal plane, which is XZ plane, unless otherwise mentioned. The main idea of this video is featured in John Dixon's book, Tires, Suspension and Handling, 2nd edition. Let me introduce the contents of this video. First, we will look at the force to find the force roll center FRC. Then we will look at the idealized spring model and kinematic roll center KRC, jacking force, incremental roll center height, incremental load transfer factor, jacking force and roll center, spring center, ideas for finding force roll center, and finally the lateral roll center location. Let's take a quiz. At a large lateral acceleration, what is the correct expression for a force roll center? Number 1. The kinematic roll center can be used as a force roll center. Number 2. The lateral force acting on the force roll center will cause a roll of sprung mass. 3. The force roll center should be at a height that allows the force to be applied laterally without causing a roll of sprung mass. Please choose one of these correct answers. First, let's figure out what force you need to use to find the force roll center. In our last video, E0077 roll center part 9, I explained the roll angles, the suspension and tire roll stiffness, and based on the forces acting on them, we could formulate equations for 6 elements of load transfer. Equation 1 represents the 3 load transfer elements at the front axle, and equation 2 represents the 3 load transfer elements of the rear axle. The load transfer elements used to find the roll center in this video are elements 2 and 5, which act directly on the roll center laterally. In this video, we will not treat the 2 of them as separate forces, but as shown in the second term of equation 3, they will be combined into a single force that acts on the entire roll center of the vehicle. The forces involved in calculating the roll center height are very important, so let's take a closer look. First, the third term in equation 3, equation 3c, is the load transfer quantity caused by the unsprung mass mu, and is not related to the calculation of the force roll center height. When the lateral acceleration Ay acts on the sprung mass ms, the lateral force Fs caused by the sprung mass can be calculated using equation 4. The tire reaction force for the lateral force Fs can be calculated using equation for A, which is the sum of the left wheel reaction force Fiy and the right wheel reaction force Foy, and can be expressed by equation for A. The moment caused by the lateral force Fs with respect to force roll center can be divided into 2. First, there is the moment caused by the moment arm h of the lateral force Fs, and the moment caused by the horizontal displacement d of the sprung center of gravity MSCG. These two are both moments about the force roll center. And the load transfer, delta FZSM they generate, can be expressed by equation 3a. The second is the moment about point C with moment arm HRC caused by the lateral force Fs acting directly transversely, and the load transfer delta FZSL caused by this moment can be expressed by equation 3b. To illustrate this, the lateral force Fs is shown twice in the figure. The force relevant to calculating the roll center height is the second term of equation 3 as explained earlier. This force is transmitted only through the suspension links, not through the spring, and can be calculated by finding the components of the vertical force Fz and the horizontal force Fy acting on the tire road surface, which coincide with the force action lines of the suspension links. This was explained in the previous video E0078, Roll Center Part 4. All forces and tire reactions used throughout this video are the forces on the sprung mass and tire reaction forces. The force on the unsprung mass, represented by equation 3c, and the tire reaction forces on it should not be used. The force associated with the unsprung mass should be ignored or subtracted. Let's review the idealized spring model. Up until the previous video, Roll Center Part 9, we examined the roll center when the left and right suspensions are symmetrical and lateral acceleration is small. When lateral acceleration is small, the geometry of the suspension links doesn't change significantly. When the suspension is symmetrical, the roll center is located along the vehicle's central longitudinal plane. Therefore, we can analyze the forces acting on the links using kinematic methods to determine the roll center. In contrast, this video will examine the roll center when lateral acceleration is high, significantly changing the geometry of the suspension links. We'll also explore methods for determining the roll center of asymmetric suspensions in the next video. In these cases, we'll also use the idealized spring model, as explained in the previous video, E0078 Roll Center Part 4, finding the roll center location by force. The key feature of the idealized spring model is that it separates the forces acting on the tires into the forces acting on the suspension links and the forces acting on the springs. When a lateral load acts, the moment caused by the sprung mass about the roll center is transferred to the tire through the spring, and the force Fs acting directly in the lateral direction at the roll center height by the sprung mass is transferred to the tire through the suspension links. First, let's review the idealized spring model when a small lateral force is applied. In the figure, Fs represents the lateral force caused by the lateral acceleration Ay acting on the sprung mass Ms, as shown in equation 4. In addition, Ftl represents the load transfer caused by the force Fs acting directly and laterally at the roll center height. The moment equilibrium equation at point C can be expressed as equation 5. Equation 5 expresses the load transfer Ftl in terms of the roll center height HRC, the lateral load Fs due to the sprung mass, and the track T. The figure also shows the case when the lateral force is small and the suspension geometry does not change significantly compared to the static state, so the difference in the angle between the left and right tire contact points and the roll center with the road surface can be ignored. In this case, the difference in the magnitude of the forces acting on the left and right wheels can be ignored, and the load transfer is relatively small, so the kinematic roll center can be obtained as shown in the figure. When lateral forces are small, the kinematic roll center and force roll center are in the same location. However, when lateral forces are large, the suspension links become asymmetrical, and the kinematic instant center, KRC, is no longer considered the instant center. Let's explore why. When the lateral acceleration is large, the difference between the outer wheel lateral force FOY and the inner wheel lateral force FIY gets larger so that it cannot be negligible, and this difference generates a jacking force that supports the sprung mass. If the jacking force acts vertically at the kinematic roll center, the sprung mass will roll. In addition to the roll motion of the sprung mass, the jacking force also causes the sprung mass to displace up or down, and the suspension geometry changes, so the sprung mass will rotate and translate simultaneously. Since the roll center is by definition a point where a lateral force can be applied to the sprung mass without causing suspension roll, the kinematic roll center KRC cannot be considered a roll center when the lateral force is large. This is because, as shown in the figure, the jacking force occurs when the lateral forces applied to the left and right wheels are different, and when these lateral forces are different, the line of action of the jacking force deviates from the central longitudinal plane of the vehicle. Therefore, if the line of action of the F jacking force in the figure does not pass through the spring center, rotational motion of the sprung mass is inevitable. If a roll of the sprung mass occurs, the idealized spring model cannot be used because the spring force and the link force cannot be separated. The spring center is a vertical line that can apply a force to the sprung mass without causing a roll. If the vehicle is symmetrical and the lateral force is small, the spring center exists at the center longitudinal plane of the vehicle. The spring center will be explained in detail later. This phenomenon increases as the kinematic roll center FRC is more located toward the inner or outer wheel. Now that we know the kinematic roll center is not a true roll center for the large lateral acceleration, let's examine the conditions for the force roll center we're looking for. As previously discussed, the kinematic roll center varies significantly depending on the magnitude of the lateral force when the lateral force is large. Furthermore, the jacking force acting on the kinematic roll center induces a rolling motion in the sprung mass, making it not a true roll center. So, where is the force roll center located? The force roll center is based on an idealized spring model and is not necessarily the instantaneous center of the sprung mass. It's important that the force transferred through the link acts on the force roll center without inducing a rolling motion in the sprung mass. This allows us to distinguish between the forces transferred through the link and the forces transferred through the spring. We use the roll center to evaluate the lateral load transfer caused by the sprung mass during cornering. To do this, we need to distinguish between the forces transferred to the sprung mass through the link and the forces transferred to the sprung mass through the spring, and the roll center is the reference point for distinguishing between these forces. Therefore, the transverse position of the force roll center must clearly indicate the moment arm h, which allows calculating the rolling moment caused by the sprung mass about the roll center and the distance d displaced by the center of gravity of the sprung mass. In addition, the height of the force roll center must be precisely located to calculate the load transfer through the suspension link, as shown in equation 5. When a large lateral force is applied to the suspension, the arrangement of the links changes and deformation due to compliance occurs. Therefore, a reference line is needed to find the force roll center. The roll angle represents the inclination of the sprung with respect to the line connecting the left and right wheel centers. The straight line and the transverse section connecting the left and right wheel centers and the central longitudinal section are the references for finding the force roll center. Looking at this figure alone, you might think that the roll center FRC of the sprung is clear. However, the track T in the figure here, which shows the state when a large lateral force Fs is applied during cornering, which is different from straight ahead running. It constantly changes due to deformation of the rubber of the joint, tire compliance, friction, and scrub depending on the magnitude of the lateral force. The force roll center FRC shown in this figure represents the roll angle and the position of the force roll center when a large lateral force Fs is applied, which changes the arrangement of the suspension links and changes the track T. First, based on this state, the force roll center will be defined as a point on the line where the cross-section including the centers of the left and right wheels and the central longitudinal section meet. When a large lateral acceleration is applied to the vehicle and the lateral acceleration increases to a larger size, the force roll center moves. The new height of the force roll center that has moved at this time is called the incremental roll center and will be explained in detail later. In general, the change in the force roll center must be considered for large lateral accelerations exceeding 0.3 g. Since the force roll center is defined as being on the intersection of the cross-section connecting the left and right wheel centers and the central longitudinal section, we will now find the height of the force roll center on this intersection. Even if we know the roll angle of the sprung mass by considering all displacements under a large lateral acceleration, the height of the force roll center cannot be determined yet. As shown in the figure, the height of the roll center varies as a sprung with a known roll angle moves in any direction, up, down, left, or right. When subjected to a large lateral force, the sprung mass can move laterally relative to the left and right wheel centers due to the suspension compliance, and can also move vertically due to the jacking force. In other words, it can move in all directions, left, right, up or down. Accordingly, the height of the roll center varies. However, regardless of how the suspension geometry changes, the height of the force roll center can be determined from the moment equilibrium equation, 5, which uses the forces caused in the links. Let's learn how to find the height of the force roll center. The second term of equation 3, which we looked at earlier, represents only the amount of force transferred through the link. Therefore, if we know the amount of load transferred in the second term of equation 3, we can find the force roll center height HRC. The amount of load transferred through the link can be found by analyzing the magnitude of the force acting on the suspension link using a computer, or by measuring the force acting on the link using a sensor attached to the link. Since it is very difficult to exactly reproduce the road driving condition of a vehicle subjected to lateral acceleration in a test laboratory, the most reliable method is to measure the force caused in the link under various lateral accelerations while actually driving on the road. The amount of load transferred through the link can be expressed by equation 5, which we looked at earlier, and if we know the amount of load transferred through the link, FTL, we can find the force roll center height HRC from equation 5. Based on what we've discussed so far, we can define the location of the force roll center. The force roll center is determined by considering all nonlinear factors related to the tire and suspension components. These factors include rubber compliance, friction, and scrub, which continuously influence the suspension geometry depending on the magnitude of the lateral acceleration. Combining the information discussed so far, the location of the roll center can be defined as follows. The roll center is a point in the center plane and the transverse vertical plane through the pair of wheel centers at roll center height. The roll center height is the lateral load transfer through the links divided by the tire lateral force, multiplied by the track. You can find this definition in John Dixon's book, Tires, Suspension and Handling, 2nd edition. Let's look at the difference between the kinematic roll center and the force roll center. The kinematic roll center can be determined by viewing the vehicle suspension as a mechanism with interconnected rigid elements and finding the instantaneous center of the sprung mass relative to the road surface. A double wishbone suspension has 8 links, 10 joints, and 1 degree of freedom. Determining the kinematic roll center requires certain assumptions. The tires and the road surface are connected by pin joints, so the track width remains constant. All links are rigid and do not deform. The tires and all joint rubbers are also considered rigid and do not deform. Friction at all joints is 0. However, in a real vehicle, tires deform, slides can occur, and the track can change. Furthermore, all links deform and joint rubber naturally deforms. Furthermore, friction occurs at all joints. When lateral forces are small, the kinematic roll center and force roll center are at the same location. However, when lateral forces are large, this assumption is inconsistent. The force roll center is determined based on force, so these assumptions are unnecessary. However, because the arrangement of the suspension links changes depending on the magnitude of the force, a different approach is required than with kinematic roll centers. Let's learn about the incremental roll center height. As previously discussed, when lateral acceleration is large, the difference between left and right tire reaction forces get bigger and a jacking force is developed, which changes the height of the roll center. To understand how the roll center height changes as the lateral force increases, we need to introduce the incremental roll center height. The incremental roll center height is defined as the rate of change in lateral load transfer through the link of the idealized spring model to the lateral force caused by the sprung mass multiplied by the track and can be expressed by equation 6. The right side of the equation is equal to the product of the track T and the differentiation of the left and right sides of the equation with respect to the force Fs. The incremental roll center height can be obtained from equation 5, neglecting the change in the track T, by differentiating the load transfer FTL with respect to the lateral force Fs, as shown in equation 7. Therefore, multiplying both sides of equation 7 by the track T, we obtain equation 8. Substituting equation 6 into equation 8 yields equation 9. From equation 9, we can see that the incremental roll center height, HIRC, is equal to the original roll center HRC plus the change in roll center height due to lateral force. The last term of equation 9 indicates that the lateral force affects the roll center height. Let's illustrate this graphically. Let's understand the meaning of incremental roll center height through a graph. As previously discussed, the height of the force roll center can be defined by equation 5. Equation 5 can be used regardless of the magnitude of the lateral force. Equation 5 can be expressed in a coordinate system where the horizontal axis represents the lateral force and the vertical axis represents the load transfer, as shown in the graph on the left. When the lateral force is small, even a small increase in lateral acceleration causes the height of the force roll center to remain almost unchanged, and the load transfer FTL increases in proportion to the lateral force. At this time, the load transfer FTL increases in proportion to the lateral force Fs, and the proportional constant is equal to the roll center height HRC divided by the track T. However, when a large lateral force of approximately 0.3 g or more is applied, the force roll center shifts. This relationship is shown in the graph on the right. In equation 6, HRC can be a small value, such that the lateral force F south is close to 0, or it can indicate a state where a large lateral force is applied. If additional lateral acceleration is applied in this state, the force roll center will move to a new force roll center as shown in equation 6. Equation 6 can also be used regardless of the magnitude of the lateral force. In equation 6, if the lateral force is small and the roll center hardly changes, the incremental roll center height, HIRC, will have the same value as the roll center height, HRC. Let's examine the relationship between incremental roll centers and incremental load transfer distribution. For clarity, the difference in roll center heights is exaggerated. As shown in equation 5, a higher roll center naturally increases the load transfer through the suspension links. Once the lateral acceleration and the vehicle's overall incremental roll center height are determined, the total incremental load transfer through the front and rear suspension links can be calculated using the wheel tracks. The distribution of front and rear incremental load transfer relative to the total incremental load transfer is determined by the heights of the front and rear incremental roll centers. Incremental load transfer increases on the side with a higher incremental roll center height. The incremental roll center location represents the movement of the roll center as lateral acceleration increases, allowing us to determine the lateral load transfer distribution between the front and rear as lateral acceleration increases. In the figure here, the case 1 indicates a larger rear incremental roll center, resulting in a greater load transfer ratio at the rear wheels than at the front. On the other hand, Case 2 has a larger front incremental roll center, resulting in a greater load transfer ratio at the front wheels than at the rear. Therefore, Case 1 tends to oversteer, while Case 2 tends to understeer. There's a misconception that understeer characteristics are induced when the front roll center is lower than the rear roll center, but this is incorrect. I'll explain this in more detail in an upcoming video. Let's find the incremental load transfer factor in relation to the incremental roll center height. The front and rear incremental roll center heights determine the load transfer distributions at the front and rear. Dividing both sides of equation 6 by the track T gives equation 10, where the incremental roll center height HIRC divided by the track T represents the non-dimensional roll center height and is called the incremental load transfer factor. The incremental load transfer factor is the incremental roll center height divided by the track and is defined as the rate of change in the amount of lateral load transferred through the link of the idealized spring model for the lateral load acting on the sprung mass. Dividing both sides of equation 9 for the previously derived incremental roll center height by the track T gives equation 11 for the incremental load transfer factor. In equation 11, the reference roll center HRC divided by the track T is the load transfer factor FL, as shown in equation 12. Meanwhile, rearranging the last term of equation 11 gives equation 13. By substituting FL of equation 12 into equation 13, we can obtain equation 14. Equation 14 is the result of dividing both sides of equation 9 by the track T, so it naturally has a similar form to equation 9. As mentioned in the introduction, there is no clearly established theory regarding the lateral location of the force roll center. However, we can deepen our understanding of the roll center by exploring methods for finding possible roll center heights. Now, let's explore how to find the force roll center using the spring center. Let's first consider the lateral location of the force roll center under small lateral forces, as shown in the figure. Assuming the vehicle is symmetrical, under small lateral forces, the roll center is located at the vehicle's center line, as shown in the figure on the left. Therefore, the angle θi between the line connecting the inner tire contact point and the inner swing center and the horizontal is approximately equal to the angle θo between the line connecting the outer tire contact point and the outer swing center and the horizontal, and both the lateral and vertical forces on the left and right tires are approximately equal. If the vehicle is symmetrical and the difference in forces acting on the left and right wheels is small due to a small lateral force, the spring center coincides with the intersection of the vehicle's central longitudinal plane and the cross-section containing the wheel centers of the left and right wheels. In this case, the kinematic roll center, geometric roll center, and force roll center all lie at the same location in the vehicle's central longitudinal plane. Next, let's find out the lateral position of the force roll center under a large lateral force. As the lateral force increases, the angle θi of the line connecting the inner tire contact point and the inner swing center with respect to the horizontal has a significantly different value from the angle θo of the line connecting the outer tire contact point and the outer swing center with respect to the horizontal, and both the lateral force and the vertical force of the left and right tires have significantly different values. For this reason, the jacking force caused by the difference in the outer wheel lateral force FOY and the inner wheel lateral force FIY in the figure on the right causes an up and down displacement of the roll center, and the line of action of the jacking force caused by the different lateral loads of the left and right wheels exists outside the vehicle's central longitudinal plane. In a symmetrical vehicle, if the line of action of the jacking force goes outside the vehicle's central longitudinal plane, it will inevitably cause rotational motion of the sprung mass. In this case, the idealized spring model cannot be used because the force acting on the link and the force acting on the spring cannot be distinguished. Therefore, the kinematic roll center obtained in this way is not the true roll center. Let's analyze the forces acting on the roll center as a force vector when a lateral force due to small lateral acceleration is applied. In this case, the kinematic roll center, geometric roll center, and force roll center all exist at the same location on the vehicle's central longitudinal plane. The figure on the left shows the lateral and vertical forces acting on the left and right tires. If we reconstruct these forces into forces aligned with the line connecting the tire road contact point to the roll center and forces perpendicular to these lines, we can express the force vector as shown on the right. If we subtract the spring forces FIS and FOS from these forces and use all the forces acting on the links to construct the force vector, it will have a triangular shape, as shown in the upper right figure. Therefore, we can confirm that no jacking force acts on the kinematic roll center. This absence of jacking force is due to the fact that the vertical components of FIL and FOL are equal in magnitude and opposite in direction. The roll center thus obtained conforms to the definition of a roll center because the forces acting on the links do not cause suspension roll. This time, let's analyze the forces acting on the roll center as a force vector when a lateral force due to large lateral acceleration is applied. In this case, the kinematic roll center exists outside the vehicle's central longitudinal plane. The figure on the left shows the lateral and vertical forces acting on the left and right tires. If we reconstruct these forces into forces aligned with the line connecting the tire road contact point to the roll center and forces perpendicular to these lines, we can express the force vector as shown in the figure on the right. If we construct the force vector using all the forces acting on the links, excluding the spring forces FIS and FOS, it will have a rectangular shape as shown in the upper right figure. Therefore, we can confirm that a jacking force acts on the kinematic roll center. The jacking force appears because the vertical components of FIL and FOL are different in magnitude and opposite in direction. Since the jacking force generates a vertical force on the roll center, it inevitably tends to rotate the sprung mass. In this way, since the forces acting on the link cause the sprung mass to rotate about the roll center obtained in this way is neither a kinematic instant center nor a true roll center. The jacking force discussed above can be expressed mathematically as equation 15 using the forces FIL and FOL acting in the direction of the kinematic roll center KRC from the left and right tire contact points, and the angles θi and θo of these forces. The jacking force is a force that supports the sprung weight in the vertical direction separately from the spring force. When cornering where large lateral acceleration occurs, the jacking force plays a role in supporting the sprung mass so that the lower part of the vehicle does not contact the road surface. This is very helpful in preventing the lower part of the vehicle from contacting the road surface when large lateral acceleration occurs in a vehicle designed with a low ground clearance to reduce aerodynamic resistance. The figure here simultaneously illustrates the kinematic roll center for both small and large lateral forces, as discussed previously. Let's review what we've covered so far. When the lateral force is small, the roll center is located at the vehicle's central longitudinal plane, and the forces FIL and FOL acting on the left and right links are equal, so no jacking force occurs. However, as the lateral force increases, the roll center moves away from the vehicle's central longitudinal plane, and the difference between the forces FIL and FOL acting on the left and right links becomes large, resulting in a jacking force. The jacking force is caused by the difference in the vertical components of the forces acting on the left and right links. In a symmetrical vehicle, if the lateral forces on the left and right wheels are different, the line of action of the jacking force will be located away from the vehicle's central longitudinal plane. Consequently, the jacking force acts on the roll center to rotate the sprung mass, resulting in suspension roll. If suspension roll occurs, the idealized spring model cannot be used because the forces acting on the links cannot be distinguished from the forces acting on the springs. For this reason, the roll center obtained in this way is neither a kinematic instant center nor a true roll center, since by definition of the roll center, the forces acting on the roll center should not cause suspension roll. Let's learn about the spring center, which will be necessary in the following discussion. The vertical line where no rotation occurs even when a vertical force is applied is called the spring center. Representative spring types include linear springs, progressive springs, and conical springs. Linear springs have a constant spring constant, as shown in the graph at the bottom left. Progressive and conical springs have a spring constant that increases with increasing compression, as shown in the upper left and upper right. Therefore, if the vehicle is symmetrical left and right and both left and right springs are linear, the spring center coincides with the vehicle's central longitudinal section. However, in the case of progressive and conical springs, the outer spring constant increases with increasing compression. Therefore, when a lateral force is applied, the spring center is formed on the outside, as shown in the figure here. Even in this case, in a symmetrical vehicle, if the lateral force is small, the left and right spring constants can be considered equal, so the spring center is located at the vehicle's central longitudinal section. However, if the lateral force increases, the spring center moves outward during the turn. When a large lateral force is caused, the spring center can change depending on the size of the lateral force, so the term incremental spring center is used to distinguish it from a general spring center. Even if both the left and right sides are linear springs, when the compression increases and the bump stop operates, the bump stop stiffness is added to the spring stiffness of the spring on the side where the bump stop operates, so the overall spring constant increases. The bump stop limits the ride height so that it does not fall below a certain height when bumping or cornering, so that the sprung does not interfere with the unsprung such as the tire, and prevents contact with the ground. When the bump stop operates, the overall spring constant becomes the sum of the spring constant of the spring and the spring constant of the bump stop. Therefore, because the spring constant increases when the bump stop operates, the spring center is formed on the outside as shown in the figure here. When the bump stop operates, the role of the shock absorber is significantly reduced, and the force input to the tire goes directly to the car body through the suspension links and bump stop without going through the shock absorber. This can cause problems with the durability of the tires and body, as both the tires and body have to absorb the force that the shock absorber should absorb. Before exploring the location of the roll center for large lateral forces, we need to define the conditions for a roll center. The roll center is defined by an ideal vehicle spring model, which divides the lateral and vertical forces acting on the tire contact points of the left and right wheels into forces acting on the suspension links and forces acting on the springs. Therefore, first, the force acting on the roll center must not cause rolling motion in the sprung mass. This is expressed in the SAE definition as suspension roll must not occur. The second consideration is jacking force. Since the lateral forces of the left and right wheels are different, a jacking force is generated, so the sprung mass performs two motions simultaneously, which are a rotational motion from state 1 green to state 2 red, and a translational motion to state 3 blue. The sprung mass can be thought of as rotating from the first green state to the current red state, and then translating from the current red state to the third blue state. In other words, the sprung mass has 2 degrees of freedom. However, if the roll center were located at the spring center, as previously discussed, the rotational motion of the sprung mass would disappear. In this state, the sprung mass does not rotate, but only translates up and down due to the jacking force. Thus, the point where the sprung mass can translate by generating a jacking force, but can transmit lateral force to the suspension link without causing suspension roll, can be called the roll center. As previously discussed, point K is not a roll center, so let's examine additional possible locations. To illustrate the general case, consider a vehicle where the sprung mass center of gravity, MSCG, is not centered on the sprung mass but is eccentric. The vehicle is shown in the rear view. During cornering, the right bump stop activates, significantly increasing the spring constant of the right wheel. Furthermore, a large lateral force is applied, causing the force on the right tire to be significantly greater than that on the left tire. Since the force on the right wheel is dominant, we can assume that the force roll center lies on the line connecting the right wheel contact point with the road and the kinematic roll center K. Therefore, if the jacking force acting at points N, M, and L does not induce a roll in the sprung mass, they can all be force roll centers. Point C is the point where the vertical line passing through the center of the line connecting the left and right wheel centers intersects the road surface. When the vehicle corners, the lateral force induces a roll in the sprung mass, causing it to tilt outward. At this time, the point where the central cross-section of the tilted sprung mass during cornering intersects the vertical line passing through point C is point N when viewed from the rear. Since the jacking force applied at point N rotates the sprung mass, point N cannot be called the force roll center either. Next, let's look at point M. Point M is the point where the vertical line drawn down from the center of gravity MSCG intersects the line connecting the right tire contact point and point K. Point M cannot be considered a force roll center either. This is because the right bumper stopper has been activated, increasing the right spring constant. Therefore, if a vertical force is applied upward at point M, the sprung mass will roll, causing the sprung mass to rotate clockwise. Although point M is vertically below the center of gravity, the stiffness of the left spring is less than that of the right spring, so the sprung mass will rotate clockwise. Therefore, point M cannot be considered a force roll center either. Next, let's look at the point L. The point L is on the spring center. As explained earlier, the spring center is a vertical line, and if a force acts along this line, the sprung mass will not roll. Therefore, if a vertical force is applied upwards at the point L, the sprung mass will not roll, and therefore the sprung mass will not rotate. Consequently, if a jacking force is applied at the point L, the sprung mass will move vertically under the force of the jacking force without rotation, and the force FOL acting through the link can act at the point L without rotating the sprung mass. Therefore, the point L can be called the force roll center. It is true that the point L is on the spring center and can be a force roll center, but there is no need to insist on the transverse location of the point L. So where is the force roll center? For the sake of explanation, the light blue dotted line on the left is enlarged and shown in the figure on the right. Since we previously assumed that the roll center is on the vertical line passing through the center of the line connecting the left and right wheel centers, the point that has the same height as the height HFRC of point L along the central longitudinal plane can be said to be the force roll center. This is because the transverse location of the force roll center is irrelevant in calculating the height of the force roll center. The transverse location of the force roll center should be a well-defined location that makes it easy to calculate the rolling moment caused by the sprung mass and the transverse location of the sprung center of gravity, MSCG. Regardless of the transverse location of the force roll center, the height HRC of the force roll center FRC must be at a location that satisfies the load transfer equation 16. Let me explain why the lateral location of the force roll center in a symmetrical vehicle is assumed to be at the midline of the line connecting the wheel centers. As we saw earlier, the kinematic roll center is not the true roll center when the lateral force is large. In the figure here, since the jacking force causes the sprung mass to roll, the location where the jacking force does not cause a roll must be somewhere inward toward the vehicle's midline longitudinal plane. One of the purposes of finding the force roll center is to calculate the load transfer for the lateral force acting laterally on the roll center, and to calculate the load transfer due to the roll angle and moment caused by the lateral force acting on the center of gravity, MSCG, with respect to the force roll center. The former is the load transfer through the link, and the latter is the load transfer through the spring. Assuming that the lateral position of the force roll center is at the center longitudinal plane of the line connecting the wheel centers, and obtaining the height of the force roll center with equation 16, the roll angle pi and moment arm h become clear, so the load transfer due to the roll angle and moment can be clearly calculated. As seen above, the load transfer for the lateral force acting directly horizontally on the roll center can be calculated with equation 16, and the lateral position of the roll center is irrelevant. Therefore, the height of the point where the line connecting the spring center and the kinematic roll center KRC and the tire road contact point R intersect can be said to be the height of the force roll center, and the force roll center height HRC obtained in this way must satisfy equation 16. reason why the spring center L is not used as the force roll center is because the displacement d of the center of mass of the sprung off the central longitudinal plane must be calculated to calculate the moment that the weight of the sprung mass generates about the roll center. The force roll center must be located such that a transverse force acting on the force roll center does not cause rotational motion in the spring center and must satisfy equation 16. By determining the force roll center so that all of these conditions are satisfied, the load transfer through the link can be calculated, and also the load transfer through the spring can be calculated using the roll angle pi and the location of the center of gravity MSCG. Regardless of how the force roll center is found, the height of the force roll center must satisfy equation 16 and must not cause rolling motion in the sprung. Although the kinematic roll center KRC is not a true roll center, it has important implications. As shown in the figure, the size of the height difference between KRC and FRC depends on the angle of inclination theta O of the line connecting KRC and the tie rod contact point R. Therefore, the larger the inclination angle theta O, the greater the variation of the force roll center due to the lateral force. Finally, let's summarize the definition of the force roll center under the large lateral force examined in this video. I've explained that the kinematic roll center is not a true roll center, and that a true roll center should not induce rolling motion in the sprung mass when a lateral force is applied to the roll center. Furthermore, I've explained that the lateral location of the force roll center must clearly represent the moment arm caused by the sprung mass, the location of the sprung center of gravity, and the roll angle. From this, we introduce the concept of a spring center, which does not induce rolling motion in the sprung mass. We define the roll center height as the intersection of the line connecting the kinematic roll center and the tie rod contact point with the spring center, and explain that the force roll center is the same height at the vehicle's center line. The force roll center height thus obtained must satisfy equation 16. The explanation so far has explained how to find the force roll center starting from the kinematic roll center and has been a process for understanding the force roll center. As previously explained, the kinematic roll center and the force roll center are completely different when subjected to large lateral forces. The force roll center can be directly determined using force without using the kinematic roll center. We can define the roll center as follows. The roll center is a point in the center plane and the transverse vertical plane through the pair of wheel centers at roll center height. The roll center height is the lateral load transfer through the links divided by the tire lateral force multiplied by the track. You can find this definition in John Dixon's book, Tires, Suspension and Handling, 2nd edition. This figure illustrates the relationship between roll center height and load distribution, which will be explained in the next video. How does roll axis inclination affect handling? What is the roll axis inclination of commercially available vehicles? Does a higher front roll center than the rear lead to understeer? Does a stronger rear shock absorber lead to oversteer? What is the relationship between stronger springs and a higher roll center? The following videos will provide all the answers. Please stay tuned for the upcoming videos. Let's find out the answer to the quiz. At a large lateral acceleration, what is the correct expression for the force roll center? First, the kinematic roll center cannot be used as the force roll center because it causes the sprung mass to roll under large lateral forces. Second, the lateral force acting on the force roll center must not cause the sprung mass to roll. Third is the correct answer. That the force roll center should be at a height that allows the force to be applied laterally without generating a roll of sprung mass. Let's summarize the content of this video. The force needed to find the roll center is the lateral force acting directly on the roll center. The force roll center can be found by analyzing the force in an idealized spring model. Using the idealized spring model, the forces acting on the tire can be separated into the force acting on the suspension link and the force acting on the spring. The requirements for the roll center can be summarized as follows. No force that causes rolling motion on a sprung must act. Forces that cause translational motion on a sprung are permitted. Depending on the lateral force size, the force roll center has the following characteristics. When the lateral force is small, the kinematic roll center and the force roll center are in the same position. When the lateral force is large, the kinematic roll center is completely different from the force roll center. Typically, the kinematic roll center can be used as the force roll center when the lateral acceleration is less than 0.3 g. Considering why the kinematic roll center should not be used, a large lateral force creates a jacking force at the kinematic roll center, causing the suspension links to become asymmetric. The jacking force causes the sprung mass to roll and translate simultaneously. When the sprung mass rolls, the road input cannot be separated into spring and link forces. If the forces cannot be separated, the idealized spring model cannot be used. If the idealized spring model cannot be used, the force roll center cannot be found. The assumptions for the kinematic roll center are as follows. The tire and the road are connected by pin joints, so the track width does not change. All links are rigid and do not deform. The tire and all joint rubbers are also rigid and do not deform. The friction at all joints is 0. In a force roll center, all assumptions of a kinematic roll center are unnecessary. The spring center is defined as the vertical line along which a force can be applied to the sprung mass without causing it to roll. The role of the roll center is, firstly, to allow the tire input to be calculated by splitting it into two types of force, the force transferred to the sprung mass through the links and the force transferred to the sprung mass through the springs. Secondly, it provides a basis for determining the following physical quantities from which the load transfer can be calculated. They are the roll angle of the sprung mass, the length of the moment arm that the sprung mass develops about the roll center, and the lateral displacement of the center of gravity of the sprung mass. Incremental roll center height has been explained. Under high lateral acceleration, if the lateral acceleration further increases, the force roll center height changes. This new force roll center height is called the incremental roll center height. Incremental roll center height should generally be considered for large lateral accelerations of 0.3 g or greater. At small lateral accelerations, the roll center height and incremental roll center height are identical. When examining the effects of front and rear incremental roll center heights on handling, the load transfer increases with the larger incremental roll center height. A front incremental roll center height greater than the rear tends to understeer. A rear incremental roll center height greater than the front tends to oversteer. The opinion that a low front roll center and a high rear roll center tend to understeer is incorrect. This will be explained in a next video coming soon. When looking at the method of calculating the load transfer through the suspension link, it is very difficult to exactly reproduce the road driving condition of a vehicle subjected to lateral acceleration. There is a method using a computer and a method of measuring the force acting on the link under various lateral accelerations. The best method is to use the computer and measurement in parallel and complement each other. The force roll center can be defined as follows. The roll center is a point in the center plane and the transverse vertical plane through the pair of wheel centers at roll center height. The roll center height is the lateral load transfer through the links divided by the tire lateral force, multiplied by the track. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0078 part of vehicle roll center, I have described the suspension roll stiffness caused by the springs and anti-roll bars together, the effect of tire roll stiffness, and the ride stiffness that includes all of these. In the latest video, E0077, the ninth part of vehicle roll center, I explained how the load transfer ratio between the front and rear wheels varies depending on the ratio of front and rear roll stiffness. Furthermore, I explained how varying the front and rear roll stiffness ratios in an actual vehicle leads to changes in the vertical load on the tires, and how the coefficient of friction, which varies with the vertical load, affects handling. In the next video, Roll Center Part 11, I'm going to discuss the force roll center change under large lateral forces, namely force roll center migration under large lateral forces, roll center height, and how roll stiffness affects handling performance, and how this relates to tuning with shock absorbers, springs, and anti-roll bars. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye, guys.